Hi, and welcome to my talk on unsupervised learning from limited data. Unfortunately, I had to change my plans and can't be there in person, but I thank the organizers for the invitation and accommodating this pre-recorded talk. I will start with a relatively obvious fact. Computer vision is constantly changing. We are now in the time of large models, as I call it. We have image representation learning on million scale data. We have Dino, MAE, SimClair, and many more models that have been trained on millions of images and produce meaningful representations that we can use for downstream tasks. We also have image and text learning on now almost billion scale data. CLIP, Stable Diffusion, Mini-GPT, and so on have been trained on billions of training samples and are very valuable tools for all the things we're trying to do. Now that we have access to these models, we have to see how we can use them. And one thing that I still find relatively puzzling is that these models have been trained on a significant portion of all the data that is out there. It's probably not all the data, but the portion is very, very large. So how can we make use of these models, and how can we use them in a way that allows us to solve tasks more efficiently? And I think we're currently in a kind of strange state. We're in a state where we have very generic models that have been trained on lots and lots of data, but we use them to solve tasks that are very specific, and these specific solutions that we are developing are very task specific and require individual fine-tuning and so on. So what I'm very interested in is how can we solve these tasks with the least amount of effort? And that means basically not adding additional labels, not collecting any additional data, and if possible, also not requiring any additional training or fine-tuning and only exploiting the models as they are, because that allows us to directly benefit from these models without a huge of extra effort. So in this talk, I will give 3 examples of 3 different ways how we can make this possible. And I think one of the more relevant trends that we have to follow in this space is to make tasks more generic. What do I mean by that? I will give an example in the space of semantic segmentation. Think about classical semantic segmentation. We have lots of training data. We collect lots of manual annotations for this data. And then we train a model that goes from images to semantic segmentation, but that model has a fixed set of classes. So in this space of making tasks more generic, there's a lot of room for improvement on this model. So people have been iterating on this over the years, and what is currently quite interesting is the space of open vocabulary segmentation, where given an image, we want to segment anything that the user gives us as input. So we have a bunch of images, and then the user specifies the things they want to segment. And you can see in these examples that the things we want to segment are usually not your typical classes from, I don't know, Coco and Pascal VOC and so on, because you have Darth Vader and so forth. So you want a model that basically takes an image and a set of probably unseen classes and outputs a segmentation for each of the classes that they got as input. Now, open vocabulary segmentation compared to semantic segmentation is way more generic, because now the task is to segment any possible class. But still, most of the existing methods use a lot of training data, because they use CLIP to bridge the text to image gap, and then they learn a model and train this and fine-tune all of their components, usually on one of the typical semantic segmentation datasets like Coco. Now, to fix this, we've been thinking about a way to basically turn these 2 red X's into green check marks. And one way to do this is to, in quotes, generate training data. Why I have this in quotes will become clear a bit later. So let's say we want to segment this image, and we're given the following typical classes that we want to segment: boat, water, sky, and mountain. Now, what we can do with the current large-scale models is we can actually generate training data for as support for this segmentation task. And there's a lot of research out there in terms of prompt tuning. In this work, we did a very simple prompt. We just use a good picture of A, and then we insert all the classes one by one that we want to segment. And with that, we basically generate on the fly a training data set, in quotes, for this image to solve the segmentation task. And then what we can do is we can use just nearest neighbor lookup in a feature space to segment this image. So how does this look like? We have these 4 classes: boat, water, sky, mountain. And from here, we just use Stable Diffusion or any other kind of generative model to generate support set images. So here is 64 images of a boat, water, sky, and mountain. Now we basically have a mini support set for each of these classes. And what we can do with this is we can run this through one of these unsupervised foreground-background segmentation methods. Here we use Cutler, but the choice is not super critical in this application. And that gives us basically regions for the foreground and background for each of these prototype images. Now, with these foreground and background separation, we basically have a way to generate prototypes. And the way we do this is the following. So we have generated these images, and then we extract features for the whole image, and we use the foreground-background segmentation. And then we just pool the features within the foreground and the background. That gives us basically for every category that we're interested in, a foreground feature and a background feature. Now we found that just pooling features completely is slightly worse than if you run k-means. So we do that and we get multiple foreground and background features for each category. And now we want to segment an image. We basically pass the image through the same feature extractor that we used before. And for each spatial location, we compare the feature to all the support set that we've generated before. And if we look up a background prototype, then this must be the background. If we look up a foreground prototype, then we can label this pixel or this region as this class. We can slightly improve on that just because when you're scaling the number of classes very, very high, there can be false positives. So you can use clip to pre-filter the set of classes that could potentially be in the image. And then you only consider the prototypes of the classes that you think might be in the image. And that allows us to segment all sorts of different things that you can usually not segment with a classical model, just because there is no training data. So there's no training data set of donuts with chocolate glaze and sprinkles. But if you use a support set generated by one of these powerful image generators, then you can generate examples that you can then directly use. And another benefit of using a very simple mechanism, like just a nearest neighbor lookup in feature space for segmentation, is that that's quite interpretable. So for every kind of object, we can query a region and ask which kind of prototypes were relevant for segmenting this region, for example, as a dog. And then we can look in our support images. So the images on the right are all generated by Stable Diffusion, and we can find the regions that match, basically. And that gives us a good interpretability of what the model thinks is happening in this image. So this is quite nice because now we've used pre-trained models without any further training or fine-tuning. So we just download them and they're ready to use. We don't need any manual annotations because we're just generating the data and automatically the way we need it, and we can segment any class. This segmentation through nearest neighbor lookup is very interesting, I think, in the sense that the pre-trained feature extractors are so powerful at this point, and if you look at the paper, we've tried a bunch of different ones. As usual, unsurprisingly, a combination of different feature extractors works best, but many of the current ones are quite similar in performance. Allows us to basically directly offload the complex training of a network to just nearest neighbor lookup, which is really, really fast as well. And I think another takeaway from this work is that with the quality of generative models that we have now, we can actually synthesize images that are good enough to allow us to get useful information from them. I put training quotes again because in this work we don't train, but there's lots of related work out there that also generate synthetic training data sets and from these generative models and use them for training. And the good thing, and this leads back to the beginning of the talk about this setup, is that basically if there's a new version of Stable Diffusion or if there's a new version of a feature extractor, we can just drop in this replacement. Since this method is completely training free, it just takes the new features or the new generated support set and it works. And I think this is more in line with this general notion of now we have these very generic models, so we should use them directly to solve the tasks instead of requiring a very long training step or any kind of further fiddling with the models until we solve individual tasks. Now I've said that this approach of making tasks more generic is only one way to align this task solving approach that we're following to these generic models that we have out there. Another way to make this work is through synthetic training data. And here I want to talk about a completely different field of computer vision, which is motion estimation. So motion estimation in recent years has been divided into two different camps. One is point tracking. This was partially revolutionized or brought back into the attention of computer vision by Adam Harley and co-authors in their point tracking work. And then, of course, a very old problem is optical flow. Now, the difference is between these two things is the twofold. One is the temporal horizon. Point tracking is usually long-term tracking. You're trying to follow one point through the video as long as you can, whereas optical flow is just from one frame to the other. But the other difference is that point tracking, as it says, looks at individual points, whereas optical flow is a dense correspondence between two frames. So you have basically a long temporal horizon, but very small spatial resolution, just one point. And in optical flow, you have a very short temporal horizon, but you can predict a very dense motion field from one frame to the next. And here's a couple of works that basically fall exactly into these categories. Now, what is interesting in this space is that both sides of this space are being trained on purely synthetic data. So optical flow is mainly trained on flying things, where these are just random 3D objects that are moving in some kind of patterns throughout these images. I've slowed these videos down because the training videos are just 8 frames long. So if I would play them in real time, they would be way too short to see anything. And recently there have been slightly better data sets with better rendering. You see that they have shadows and the objects have physics and so on. But it's basically the same thing where you have a bunch of synthetic objects that are being thrown into a scene and they interact a little bit. And since everything is synthetic, you can get perfect ground truth. Now, if we look at these two sides of temporal tracking, and we look at point tracking, where you can't see this because this is under my camera. Basically, in blue, I have background points highlighted, and in pink, they are object points. So this is single point tracking, where we start where we track each point individually, but we start with a grid of points in the first frame and follow the points along. And you can see that when you're tracking individual points, you lack global consistency. So the points drift relative to each other and nothing is really stable. Now, on the other hand, if you track with optical flow, so here you compute the optical flow from one frame to the next and you move the point based on the optical flow, that works really well in terms of global consistency, but you have a problem with occlusion. So you can see that the car collects the background points on its windshield and the front, and they're just moving with the object, because if you're just looking at one frame, you cannot deal with occlusions that are longer than one frame. So what we were looking at is, can we somehow bridge the gap between these two worlds and exploit both sides? So we want to track points for a long time, but we want to track them together. This means we get global consistency from tracking many points and they can talk to each other and there's a global understanding of the frame. But we also want to get occlusion handling from these long-term tracking tasks. And we want to keep on training on synthetic data. So the whole setup can be basically made as a change in the architecture of the model. And I want to talk quickly about how this can look like, but all the details, of course, are in the paper. So we have a video like this one, where we have multiple frames, and then in tracking, not all the points need to start in the first frame, so there's points that you are interested in that start later in the video. So here we're tracking 3 points. And then, as usual, you take a CNN and you compute some features for these images. And then you can extract what we call track features for each one of these tracks that you're trying to estimate for each of these starting points, which is a feature that basically describes what you're looking for in all of the frames. Now, since the tracking can be very long, we apply this as a sliding window scheme where we have overlapping windows so that some information can pass from one window to the next. But to understand how everything works, we can just look at one sliding window for now. So as input to the model, we have these track features, which is just a feature of the point that we want to track. And we have the 2D starting locations. And then we use these to initialize tracks, which just means we basically copy all the information across time. So we have the same feature in every frame and we have the same position in every frame, which is of course wrong, but we set up an iterative refinement scheme where the model just predicts updates to each point in time to make it fit the track that you're actually trying to estimate. And similar to how people deal with optical flow, the trick to make tracking generalized to real data is to let the model look at correlations of features, where you're basically comparing the track features that you have computed to their new locations in the other frames, and you compute the correlation. And this way, if your domain changes, this might not directly reflect in the correlation features because you're comparing two features, and even if the domain changes, the comparison of the features should still make sense. And then we add a bunch of extra features to that. So we encode the movement, we encode the visibility, and we add the correlation features, the track features, and the initial locations of the track. And obviously, we feed all this to a transformer that basically looks at all the tracks and all the points in space and time and outputs an update both to the features that we're looking for as well as to the 2D locations. And then we can feed these updated features and locations back in and have an iterative scheme where the transformer always updates the tracks until it converges. If we can do that, you can see that this basically solves both problems that the other methods had, where you are have the global consistency from tracking many points, but you also can deal with long-term occlusions because now you have a model that can actually track points over a long period of time. So you can see that the background points do move behind the object and stay in the right place, even though they are occluded for a long time. Of course, there's some problems. You can see there's tracking the shadow under the car and the points are moving with it and they should actually be staying. But the big problems of the approach have been solved. Here's a couple of examples where the color is just spatial location. That makes it easier to keep track of the results. You can see that it's relatively stable, the way we can track things. Here's an example that works well, but of course is not perfect. But I put this here because I always find it fascinating that a model that has been just trained on some random objects colliding on a synthetic 3D plane can still learn to track points like this on a real image, even though it has never seen any deformation or anything like this seen at all before. And this is one of the main advantages of this setup, basically, that since you're operating on these correlations between features, you're much more likely to generalize to unseen data because the features will change, but the correlations might still be meaningful. And that allows you to have training data that does not have to be super realistic or in domain, and it will still work. Of course, formulating this as a transformer architecture makes a lot of sense because that allows you to track any number of points in any arrangement, and the transformer, the attention will just work. And if you want to try this model, please do so and let us know if there's any issues or problems, because we're still trying to make this as good as we can. And if there's any problems with the specific scenes you're tracking, then we would like to know. Okay, so synthetic data was the second idea to align ourselves with this very generic and generalizable pre-trained models that we have access to. And the last idea I want to talk about is something that the NLP community has figured out for quite a long time, but somehow in vision we're still a little bit behind, and that is solving tasks by prompting models. And I was quite surprised that prompt engineering, which is basically designing an input to a large model that adapts it to do the task that you want to do, is now also a job description. So if you're looking for job advertisements, you find companies that are really looking for prompt engineers. So it's a really big field, and somehow in vision we are a bit behind the NLP community that somehow is much better at prompt engineering. So how does prompt engineering work for large language models? So these large language models that everyone is using, like ChatGPT, have been fine-tuned with human feedback, and which we call user-aligned models. And then we have data-aligned models, which are basically these models before they have been fine-tuned with human feedback. And the data-aligned models discover their behaviors only from the data. So the human has not told them how to adapt to tasks that are presented in. So all they do is learn from the data that have seen in training. And the data-aligned models have often an inherent capacity to solve some tasks that are somewhat surprising. But people have discovered that, for example, for machine translation, there's enough data out there that allows the model to pick up representations that are useful. So here is a sample that was discovered in the training data of GPT-2, where basically a sentence contains both the English part and the French translation of the sentence so that the model can learn a representation that can actually translate. If you do user alignment for these models, they somehow lose some of their ability to adapt to the prompts. Now, how do we do prompt engineering in computer vision? And one thing we've been thinking about is, how do humans interact with image-text pairs? And the obvious answer is that we usually annotate images manually to draw attention to a particular region. So if I want you to see that there's a mountain lion in this picture, I rather draw a red circle around this mountain lion, otherwise is very difficult to spot. And this red circle seems to be very prevalent. So if you go on YouTube, you find hundreds of tutorials that show you how to actually add a red circle to a video. And then if you look further, on Reddit, there's a whole community that with 35,000 members that talks about images where somebody added a red circle that has been useful. And of course, there's also the opposite community with even more members that complains about images where a red circle has been added, but it was completely useless because it is obvious what is already shown in the image without the circle. So how can we make use of this? And the way we do this is the most simple thing we could think of, and that's basically we just draw circles on the image and use one of the vision language models to evaluate whether this circle is placed in a meaningful way. So, for example, you can take clip and a text query, the cub on the right, and then you draw a bunch of circles in the image, and then you rank the images based on their clip score. And then what we found is that the image where the circle is placed in the right location will rank highest for clip. And that is quite interesting because it seems like adding these red circle to the image steers the embedding space of clip. And looking at how well this works for different models, we find that models that have been trained on larger data sets, so on the right you see models trained on Lion and on WIT, which is 400 million data, and they seem to respond much better. So on the x-axis is ImageNet zero-shot classification score, and the y-axis is our task, whereas the big models benefit much more from, or our task benefits much more from the models that have been trained on large data. We also trained a little classifier that tries to search these training data sets for images with red circle, and we found several examples where red circles are in the image, and we think that the larger the training data set, the more chances of this is that this will occur, and then that's how the model can learn how to deal with red circles. There's one part that I find very interesting and that we always have to keep in mind when we're using these large models that somebody else has trained, and that are ethical considerations. And we found that when you add a red circle over a person, there's a very strong bias in CLIP, at least, to classify this person as either a criminal or missing. So here is one image, and we rank the 4 words based on their clip similarity with the image. So woman, man, missing person, murderer. And if you just use the image without a circle, you rank woman, man first, and then missing person and murderer. But as soon as you draw a circle around the person on the right, murderer and missing person ranks top. And if you draw a circle around the left, missing person and woman ranks top. Which means there's clearly some news data that went into training CLIP, but we should be very careful when we're using these pre-trained models in our tasks, because we're inheriting all these biases, even though we don't know that they actually exist. So this is something we stumbled upon on accident, and we didn't know that this was the fact. So if you're using pre-trained models, make sure that you are aware of these ethical considerations. By the way, this is a paper that will be presented on Thursday. So if you want to know more, please come to the poster or oral session. So to conclude this talk, I hope I have convinced you that since computer vision is moving towards these very generic pre-trained models that we can all use, we should also adapt the way we solve tasks. We should use these models that we have that become more and more general purpose to solve tasks that are also more and more general purpose. So we have to make the tasks that we're solving more general so that they can be applied to way more different applications than we are currently doing. And that also basically means that we should solve tasks with less effort, because the more effort we put in to adapt the pre-trained models to the specific solution that we're looking for, the less general this becomes, because whenever the pre-trained model changes, you have to go through all the steps to then make your task work. But of course, this I think should become easier as we go on, because we have many tools that allow us to do this more and more efficiently. So we have synthetic data, we have very strong generative models, and we have better and better features that become more and more useful for all sorts of downstream tasks. Thank you very much for your time, and I hope you enjoy the rest of the workshop and the conference.